This is part 1 of our AP class treatment of the gas laws. Unlike solids and liquids, gases have 4 measurable properties that can change: their pressure, their volume, make them smaller, their temperature, we know as they warm up their density decreases, and amount, number of moles, which is why when a balloon leaks, it loses volume. So we're going to need to talk about all 4 of those. Now, pressure is a force exerted over a particular area, and therefore it is defined mathematically as the force in newtons divided by the area. The conversion units that we need to be aware of are the Pascal, which is the SI measure of pressure, is a Newton over a surface area of 1 square meter. So it's in newtons per square meter. That's actually not a huge pressure. An atmosphere is defined as 760 millimeters of mercury column in a Torricelli barometer like the one you see diagrammed here. At 1 atmosphere, the pressure on this well of the element mercury forces mercury into a vacuum tube, into an empty tube, to a height of 76 centimeters or 760 millimeters. And the millimeter of mercury is also called a torr. An atmosphere is also equal to 101,325 pascals, or 101.325 kilopascals. We usually just say 101.3. So those are units of pressure you may see in problems. There are 2 kinds of manometers that can be used to measure gas pressure. This first one here is like the Torricelli barometer. That is, you're measuring the gas by a liquid, usually mercury or xylene, that is pushed up into an evacuated tube. It's very rare to see one of those. In fact, I have never seen one of those in operation. The other kind of manometer you will more frequently see in chemistry and physics labs is a U-tube that is open to the air. And so whereas over here with the vacuum type barometer you get an absolute pressure, here you get a pressure that is relative to the pressure of the atmosphere pushing down here on this column of liquid. So open manometers measure relative pressures, whereas closed manometers measure absolute pressures. This is the apparatus, the original Boyle design of the apparatus used for studying the relationship between pressure and volume of a gas at constant temperature. As you see, there is a gas here, and he used mercury. There is mercury here in the U-tube, and originally you start off with the volume here of the mercury such that the levels are the same, and therefore the pressure is the same as atmospheric pressure. Now, Boyle then added mercury and increased the height, and you'll notice that the height of the gas column, and therefore the total volume, has decreased. Adding more mercury decreases the volume of the gas more, and finally here we see a very tall column of mercury pushing on the gas. And so as he added mercury, he increased the pressure and decreased the volume of the gas. As pressure increases, volume decreases. Boyle worked out a mathematical relationship by studying the curve here of pressure versus volume, and you can see that this is a reciprocal relationship. The pressure on the gas is proportional to the reciprocal of the volume, and at each point on this curve of pressure versus volume, if you multiply the pressure, like 0.6 atmospheres, by the volume, here 2 liters, you get the same constant pressure volume product at each position on the curve, so that 0.3 times 4 is the same as 0.6 times 2. Boyle found the pressure times the volume of a gas is a constant. If we would take any 2 points on this line, then we would see that P1 times V1 here is equal to P2 times V2, for instance, here or here. And that is the useful mathematical expression for Boyle's law. Boyle kept the amount of gas and the temperature constant. Was this what he should have controlled to study the behavior of pressure and volume? Over here we see the straight line that results from graphing the pressure versus the reciprocal of the volume. So here's a practice problem for you. If a sample of chlorine gas occupies a volume of 946 milliliters at a pressure of 72.6 kilopascal, what would be the pressure if the volume is reduced at constant temperature to 154 milliliters? So try to solve that, and then after you turn the video back on, you can check your work. So here's our usable P times V equals a constant. And we have a pressure of 72.6 kPa, volume is 946 milliliters. To start with, we're looking for P2, and we know that V2 is 154 milliliters. The first thing you do is you solve for your question mark. Solve how many kPa? Well, you're going to have to divide both sides by V2, and you get this expression. Then you can plug in your numbers and units, and don't forget the units, and do your arithmetic. Milliliters over milliliters is 1, and the answer is 446 kPa. That makes sense because the volume is much lower than it was to start, and therefore the pressure should be that many times larger. Here's another question, and we start with the same formula and different numbers. We're looking for V2. We solve for V2 by dividing both sides by P2. We can then plug in our numbers in units. Atmospheres goes away because of the various things that we can do to get that to V1. And we multiply and divide, and we get 1,560 milliliters, or 1.56 liters. Now, if we take a gas, air will work, and I did this back in college. You add a few drops of mercury to a capillary tube, it will actually trap the gas, and if you keep it in, say, an ice water bath at low temperature, you could have a thermometer in there with it to measure the temperature. You could see that when you put it in a warm water bath, the gas expands. And we know that's because the molecules of gas are moving faster. So answer the question, what does using a good seal here control, and what does a constant mass on the seal control? So the constant mass on the seal is the pressure of the mercury droplet. So as we study the volume of the gas versus the temperature, we see that as temperature increases, the volume also increases. And at various situations, if you keep the amount constant and the pressure constant, and you can study it at different pressures as we did here, you see a straight line. We have to extend or extrapolate the line back, and we get an absolute zero where the volume would theoretically be 0 milliliters at negative 273.15 degrees. So the volume is proportional to the temperature measured from that point only, the absolute temperature, and we can say that the volume then is a constant, here's your slope of these lines, times the absolute temperature. We can also say that V1 over T1 equals V2 over T2. For any one of these lines, the volume divided by the absolute temperature at any point here is the same as the volume divided by the absolute temperature at any other point on that line. And the temperature in Kelvin is always the Celsius temperature plus 273.15. Here's another problem we can do. We've got the volume of the helium, we've got the Celsius temperature, and we want to know what the temperature would have to be to have a smaller volume of 1.54 liters. We start off with our easy mathematical expression, remembering here to add 273.15 to the temperature. We can assume 2 digits after that would be 0, and we're always in Kelvin. Volume 2 is 1.54. We expect the new temperature to be lower, and so we solve for T2, which is what we're looking for, and we see that it's V2 times T1 over V1. I find to do this derivation, it's easier to start up here with T1 over V1 equals T2 over V2. Then all I have to do is a simple multiplication, and you've got your expression set up just like this. We then put numbers in units in, and we end up with the liters going away and at 219 Kelvin. If that's what we're asked for as Kelvin as an answer, then that's fine. Otherwise, we can subtract 273 and get negative 54 degrees Celsius. Avogadro's law. What must be held constant to study the volume as a function of the number of moles of gas? You did this experiment in first year. Volume we find is proportional to the number of moles. The volume therefore is a constant times the number of moles. V1 over N1 equals V2 over N2. This is a straight line we're working with. So here's a problem. At constant temperature and pressure, if 3.2 grams of oxygen is added to 4 grams of oxygen in a balloon, to what volume will an original 1 liter expand? Note, we are adding gas, just like we would in a normal, fun adding to a balloon's volume. So we solve this equation here for V2 by multiplying by N2, and we get this V1 times N2 over N1. We plug in numbers in units, and we get 1.80 liters. It's expanded, just like we wanted. Now note, we had 7.2 grams as our total here because we added to the original 4 grams. And we have to keep aware of how the problem is structured. So answer the question that is asked. Avogadro's law then can be used as a basis of stoichiometry because we can see easily, because of Avogadro's principle, that if 3 molecules react with 1 molecule here to form 2 molecules of ammonia, then 3 moles, the mole ratio is the same as the molecule ratio, and at constant temperature and pressure, the volume ratio is the same as the mole ratio. We just read the volume ratio right off the coefficients of the equation. So here's one last problem for you to do. And go ahead and read that, turn off the video, and we'll look it over when you come back. Here's your equation, balanced equation, showing that 4 moles of ammonia produce 4 moles of the nitrogen monoxide. Therefore, 1 mole of ammonia produces 1 mole of nitrogen monoxide, and the volume ratio and the mole ratio are the same. So we set it up like this. Number of liters of NO is equal to 2.5 liters of ammonia times the ratio, which we got from the equation, 4 liters of NO for 4 liters of NH3, and the result is 2.5 liters of nitrogen monoxide. You can continue this on part 2.